Everyone, this is going to be section 9.5 on content subsets and combinations. So first, let's define what is a combination. An R combination of a set of n elements is a subset of size R chosen from the set, and the order here is not going to matter. The number of R combination of an n element set is often denoted by this symbol, which means n choose R, or choosing R out of n. Let's give an example. Consider the set of 4 names: Anne, Bob, Sid, and Dan. We're going to get now 3 combinations of those 3 names. So we're always going to leave one person out each time. So this is going to give me the following sets. First, the set of Bob, Sid, Dan. Second, the set of Anne, Sid, and Dan. Third, the set of Anne, Bob, and Dan. And finally, the set of Anne, Bob, and Sid. As you can notice, because we're choosing 3 out of 4, we're essentially going to have 4 ways of doing this. This is also can be considered in another framework, another context, as the number of ways of forming a size tree committee out of 4 people. Now, let's go back and think about permutations and compare them with combinations. So if you remember, in permutations, the order kind of matters. So if you had this set of 0, 1 and the set of 1, 0, those are going to be considered different. The number of permutation is given by the formula n factorial over n minus 1 factorial when we're thinking about permuting R of n elements. In the combination is not order. Order doesn't matter. So 0, 1, and 1, 0, they're essentially the same because they're picking the same elements. And so the number of combinations here is going to be a little bit more lean. And if we pick n choose R, then that's going to be represented by n factorial over R factorial times n minus R. So this means that for the total of n factorial initial combinations, you're removing more things here. Because you're removing everything that is repeated. Since the order doesn't matter, everything that shows up repeated is going to be essentially the same thing. Now, there's key relationship here between combinations and permutations. For example, the permutation can be seen as the combination times R factorial. And in a similar way, the combination can also be seen as the permutation divided R factorial. So there's the relationship there between these 2 formulas. One example of this is like, let's consider the 2 combination and 2 permutation of the set 0, 1, 2, 3. First and then let's go with a combination. So let's choose 2 elements out of those 4. So I can do this in 4 out of 2 ways. And step number 2 is if we're going to order to get a permutation, then notice that because we're ordered 2 elements, we get to do a 2 factorial, which is 2 ways per subset of order this out. By the multiplication rule, then the number of permutations of 2 elements out of 4 is just going to be, I can choose 2 out of 4 and then order it in 2 different ways. Now, we know that the permutation of 2 elements out of 4 is 12. So I can actually find also how much is 4 choose 2 using the value of the permutation. The permutation of 2 and 4 is going to be 12 divided by 2 factorial, which is 2, is going to give me 6. Which kind of makes sense if you think of all the subsets of size 2 without repetitions. Like, for example, 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, 2, 3. That gives me all the possible combinations with the order doesn't matter here. Now, the formula for n choose R has a couple of particular things. Notice that R is a number that is bigger than 0 and less than n. It gotta be a smaller number because we're choosing R out of n, so n gotta be a bigger number. We gotta get used to making some calculations with the combination formula. So for example, phi choose 2 can be represented as 5 factorial times 2 factorial times 3 factorial. But for computations, sometimes the bigger factorial can be broken down so you can cancel out some stuff. So for example, I can see 5 factorial as 5 times 4 times 3 factorial. And so you get to cancel this 3 factorial here, and this simplified to times 5 times 4 divided by 2, which is going to be 10. I can do that with much larger factorials. So for example, here we have 10 choose 3. That is 10 factorial divided 3 factorial times 7 factorial. And then we can break down 10 factorial as 10 times 9 times 8 times 7 factorial. Canceled out that 7 factorial. And then we get 10 times 9 times 8 divided by 3 factorial, which is 6. And so that's 720 divided by 6, which is 120. Some normal formulas that you can remember is that if you do n choose 0, that's going to be 1. N choose n is going to be 1. And n choose 1, that's going to be n. You can confirm that these formulas are actually true just by applying the definition of the formula. Now, let's go to permutation with repeated elements. So when a set has repeated elements, some orderings are identical, and we divide the factorial by each of the repeated counts. So for example, the multinomial formula will help us set this up with considering that we have a set of n objects with n1 copies of type 1 and 2 copies of type 2, so up to nk copies of type n or type k. Where the sum of those n1 up to nk is going to be equals to n. And so when we have those objects with repetition, we can see the arrangements of those as n factorial over n1 factorial times n2 factorial times up to nk factorial. So all the repeated elements are removed from the copies. So one example of that will be, let's arrange the letters in level. So notice that level has 2 L's, has 2 E's, and has 1 B. So a total of 5 letters. But out of those 5 letters, because we have repetitions, then the total number of arrangement that I can do of those letters is going to be 5 factorials by the total of letters, divided by 2 factorials by the number of L's, 2 factorials by the number of E, and 1 factorial by the numbers of letters B. So this is like 120 divided by 4, 30 distinct arrangements of the letters in level. A more complex one will be, let's think about Mississippi. So if we do Mississippi, I have 1 M, but I have 4 I, 4 S, and 2 P. So in total, we have 11 letters here. So yeah, 4, 8, 11. And so we can go on the order 11 factorial divided by 1 factorial, 4 factorial, 4 factorial, 2 factorial. And that's going to give me like a total of 34,650 different arrangements. All right, so in summary, we learn about R combinations, which is an order selection of R elements from n the same as a subset of size R. The combination formula is given by the n choose R, which is in terms of factorials, is related to permutations, and you can obtain the values of the permutations if you're adding all the possible arrangements that are repeating themselves. The n choose R also counts as the number of R element committees, R element subsets that you can pick, or ways to choose R items out of n when the order doesn't matter. And we have the multinomial formula for repeated elements, where we can get distinct arrangements of n objects with repetitions. Be very careful when you're using permutations. Permutations are using when the order does not matter. So you use permutation when the order does not matter, that you're going wrong. Committees, subsets, and groups are in order, and you need to use combinations for them. Ranking sequences and arrangement are order, and so you need to use permutation in that scenario. When order matter, you use permutation. When order doesn't matter, you use combination. Be careful also with the formula if you forget to divide by r factorial. The formulas of permutations and combinations are similar, so you gotta be careful with that. And be very careful with arithmetic errors when you're calculating. You might very easily slip one number of two when you're canceling factorials before multiplying. All right, next we're gonna go with combinations, but with repetitions of elements.